Ever wonder why we do constant acceleration? Well, here's the reason why. Free fall is going to be a special case of a constant acceleration. This is why we have all our equations deal with just a constant acceleration, so we don't have to worry about it changing. We deal with this every day. We live on a big planetary mass, Earth, and we've discovered that everything over the years falls towards the center of the Earth at a constant acceleration. Aristotle was wrong. For about 2,000 years, Aristotle and humans believed that his physics was correct. Galileo finally solved the problem. You ever see a leaf or an acorn fall from a tree? Clearly, you'll see the acorn hitting the ground first. So based on this empirical evidence, lots of years of experience, Aristotle concluded that heavy things fall to the ground at a faster rate than lighter things. Aristotle did not account for air resistance. Genius of Galileo was to see through this, and he conducted many experiments to prove Aristotle wrong. Legend has it that Galileo took 2 cannonballs of different weights to the top of the Leaning Tower of Pisa, and he repeatedly dropped them. He constantly showed all the people that were watching that the cannonballs hit the ground at the same time. Since cannonballs are made of similar materials like lead or iron, and they're approximately the same size, even though they might be different masses, you could think that the cannonballs would not be affected very much by the air resistance. Consequently, they would hit the ground at the same time. Galileo was able to see through the confounding force of air resistance, and he was able to determine that the acceleration due to gravity of freely falling objects is about the same. This value occurs so much in physics we give it a special name and a special variable. The acceleration due to gravity is given by this. G sub e, meaning G on Earth, is 9.81 meters per second squared. That's close enough to 10 for us, so let's use 10 meters per second squared in our calculations. We often omit the subscript e, and we just call the variable g, and like I say, let's just use 10 because 10 just makes it so much easier to calculate. We can live with a 2% error in our calculations. Near the surface of the Earth, in the absence of other forces, freely falling objects will accelerate towards the center of the Earth at approximately 10 meters per second squared. The direction is always towards the ground, and in most traditional coordinate systems, up is positive, so the negative sign would indicate a direction. What does this mean for our kinematic variables? We already know the equations. The same 4 equations we used before are going to be exactly the same ones we use now, with just some minor changes. To distinguish between the horizontal and vertical motion, I replaced x variables with y variables. And then I replaced any acceleration with negative g. In our coordinate system, again, with up being positive, objects thrown up slow down, so the acceleration has a negative sense. Similarly, objects dropped down are speeding up, again with a negative acceleration. So here are the 4 kinematic equations for free fall. They should look very, very familiar with you. All I did was take the original ones, replace any x with a y, and replace any a with a minus g. I've also added a little additional subscript for the velocities, so I have v initial y and v final y. Those are what those other ones mean. In 2-dimensional motion, we will also have x motion and y motion, so we sometimes need to distinguish between the two. That's why I have the y subscript. Of these equations, 1, 3, and 4 are particularly useful. We rarely use equation 2 in this case. In the equation, wherever you see a g, use 10. We've already put the minus sign in the equations, so please don't add another minus sign. With these kinematic equations, we can find some special times and special locations. First, we can find what I call time to top, or TTT. This would be how long in time it takes an object to reach its highest point. We know that while it's going up, the velocity is positive. When it's coming back down, it's negative. So somewhere it had to cross through 0. That 0 velocity for its y velocity must be where, or at that time, must be when it's at its highest point. So if I set that equal to 0, I get 0 equals v initial y minus gt. Solving for that specific t and calling it TTT, I find that time to top is equal to the v initial y divided by g. If we know the initial upward velocity, we can calculate TTT. Of course, if we live on a different planet, g would be different, and I would have to give you what that g value was. We'll assume we're on Earth, again, unless I explicitly tell you otherwise. If you plug the TTT into the y equation, you can find the maximum height, which I'll call y max. Here, y max is equal to y initial plus v initial y squared, that divided by 2g. If you start at ground level, your y initial is 0. If you're on a cliff or in a hole, y initial is not 0. On a cliff, it would be positive. In a hole, it would be negative. We can also find time of flight, which I'll call TOF. This is the time that the object is actually in the air. This is a little bit more complicated. When the object hits the ground, we know that our y final is 0, so I'll take my y equation and set it equal to 0. Here's the equation. 0 equals y initial plus v initial yt minus 1/2 gt squared. This is a quadratic equation. As I like to say, embrace the horror and realize you're going to have to solve this. It'll almost certainly not be factorable, so don't even try that, so you'll probably have to use the quadratic formula. Here's the quadratic formula. In our example, a is equal to minus 1/2 g, b is the v initial y, and c is the initial y. If you're on Earth, then the a value becomes minus 5. You should remember from math that the quadratic equation does have two solutions. Sometimes one of the answers is negative, sometimes it's positive. We'll always ignore negative values. Negative values for time don't have any physical meaning. In the odd situation where you're in a hole, that means you start with your y initial less than 0, you could get a solution that has two positive answers. Think about what that would mean. You reach ground level on the way up out of the hole, you go higher, and then you finally come back and hit the ground when you finally hit the ground. So you could have two positive values. In that case, the second positive value would be time of flight. If your v initial y is 0, you don't have to use the quadratic formula, as the equation can be solved and you'll have two positive equal roots. Using the quadratic formula is not easy, you know that, but it's something that I insist you be able to do. Don't try to put the whole thing in your calculator at once. That's probably really hard to do. I would do smaller chunks. I would do what's under the radical sign first, making sure you pay attention to the signs, and then remember to divide the entire numerator by 2a at the end. Here's an example problem. You're on a cliff that's 87.3 meters tall. You throw a baseball up with initial velocity upward of 14.5 meters per second. I would like you to determine TTT, y max, time of flight, and the velocity the baseball hits the ground with. Time to top is easy. We just really put numbers in. The initial y divided by g, that's 14.5 divided by 10, or 14.5 seconds. Now to find y max. That's again also easy. Put all the numbers in. I'm going to get my y initial, which is 87.3. Oftentimes people forget their y initial. To that I have to add the 14.5 squared divided by 20. If I put all the numbers in there, I get 97.8 meters. If you forgot the original y initial, you would get 10.5. What that's telling you is that the ball went 10.5 meters above the top of the cliff. We usually measure our y max from the ground, so that's why we include the 87.3. Next slide will show you how to solve the other ones. Here's our problem again. To solve time of flight, I have to set the equation equal to 0. Here's what I get. 0 equals 87.3 plus 14.5t minus 5t squared. A is minus 5, B is 14.5, C is 87.3. This is not factorable. You're going to have to use the quadratic equation. Putting things in, this is what it's going to look like. It simplifies to minus 14.5 plus or minus 44.2, all of that over minus 10. Simplifying, I get 27 or 29.7 over minus 10, or minus 58.7 over minus 10. The first answer gives me a negative time. We ignore that one. The second one gives me a positive time, 5.87 seconds. That's going to be my time of flight. Make sure you can get this answer. I want to make sure that you can put these numbers in your calculator and be able to duplicate my work. We'll ignore any negative times, as I said before. Continuing with the problem, I want to find the velocity that the baseball hits the ground with. Now I can solve for this. Oh, my v final y is equal to my v initial y minus gt. Putting in the numbers, I get 14.5 minus 10 times the 5.87. That's going to be the time I put in there because that's the time of flight. Putting that in, I get a minus 44.2 meters per second. That's a negative number. That should make sense to you. The object is falling. It should be moving down. I don't see how you can hit the ground with a positive velocity. It would be moving up at that point. So make sure that that all makes sense. Sometimes problems can simply have very easy solutions. That means, in the special case, where you start and end at the same level, you're going to have the following situation. In that case, my time of flight will equal twice the time to top. What does that mean? It means the same amount of time it took you to get to the top is the same amount of time it'll take you to fall back to the ground. You'll end up at the same level. You still have to find time to top, but time of flight is easy to calculate. Remember, this equation will only apply if you start and end at the same height. Now, the other neat thing is your final y velocity will equal negative your initial v velocity. Whatever velocity you lose on the way up, you regain exactly that on the way down, just in the opposite direction. It's falling, so it will be negative. Again, remember, this simplification only applies if you start and end at the same level. Here's a sample problem where you start and end at the same level. In this case, it'll be the ground. You launch a cannonball straight up in the air. It lands on the ground 43.2 seconds later. Calculate time to top, v initial y, time of flight, and v final y. You already have the time of flight. It's given in the problem as 43.2 seconds. That's easy. I can use that to calculate time to top. Time of flight is 2 times time to top, so time to top is 1/2 of time of flight. 43.2 divided by 2 gives you 21.6 seconds. You can use the time to top then to find the Vy initial. Time to top is equal to V initial y divided by g. Rearranging that equation gives your V initial y equal to g times time to top. That's going to be 10 times 21.6. That gives me 216 meters per second. Well, if you start and end at the same level, then your final y velocity is just going to be negative that, or minus 216 meters per second. Finally, you can calculate y max. Y max is going to equal y initial plus v initial y squared divided by 2g. You start at ground level, so the y initial is 0. 216 squared divided by 20, I get 2,330 meters. And that's pretty high, but we did shoot the cannonball up with a pretty large initial velocity. That's it for free fall in one dimension. We're throwing things straight up so that they come straight back down. It will get a little bit more complicated in 2 dimensions, but not significantly. And the equations you've learned here will still apply to 2-dimensional kinematics as well. Remember to practice with the quadratic formula. Remember how to calculate time to top, y max, and time of flight. They're easy calculations. You should be able to do them. Remember the simplifications you get when you start and end at the same level. Those equations for time of flight and final y velocity only apply when you start and end at the same level. Otherwise, you have to use the original equations to calculate them.